Yeah, we usually start
No
at
worries.
So maybe we can start.
Perfect.
I will just say a few words. Thank you very much for accepting to present. So Frano Rajič is a PhD student in EPFL. Is it still the case?
Sorry, what?
So you
VLG, yes.
In EPFL, working in the computer
EPFL.
vision group. And so he had a paper recently about point tracking in 3D, in 4D, and I found it very interesting. So thank you, Frano. The stage is yours.
Thank you very much for the introduction. So today I'll introduce you to multi-view 3D point tracking, and this work here is the result of a collaboration between ETH, Belgrade, CMU, and Microsoft. So the world we live in is dynamic, and as humans, it's very easy to understand how things move and deform and change over time. But I argue that for intelligent agents, this perception is also very important for them to then interact with the environment and solve various tasks. Having this perception of how things are changing, of the dynamics, enables then applications in robotics, as well as in a surgical room for intraoperative assistance, and more generally in biology and neuroscience for tracking arbitrary points and analyzing the movement, for example, of animals, etc. For these applications, it's very important that the method doing the point tracking or the understanding the dynamics is efficient, especially for robotics, so it needs to be run very fast. It also needs to be precise. That's important for all the applications. What's also important is that the method is robust to the number of cameras, of how these cameras are arranged in the 3D space. For example, if you have more cameras, we expect a better precision. So let me first give you an overview of the problems in computer vision related to this. So these fall into point correspondences in 2D as well as in 3D. So starting with 2D problems, you have feature matching, very important problem, which is very well studied and enables many applications in 3D reconstruction, in SLAM, etc. However, it's only checking static points. Moving to dynamics, you have optical flow, which is tracking the apparent movement, the apparent motion in videos. It's tracking dynamic points, but only from one frame to the next frame. So it's short term. Point tracking is the problem which tracks the point throughout the whole video. For example, if you're starting on the first frame or somewhere in the middle, you want to track the pixel throughout the whole video. This is an all tracker. Recently, it was the state-of-the-art point tracking method. It's tracking dynamic points and in the long term. Similarly, in 3D, we have scene flow, which is an extension of optical flow, and it's tracking the apparent motion in 3D. Also, we have a monocular 3D point tracking, which has received a lot of attention recently. And it's tracking points in 3D, in world space, or in camera space. However, it can't leverage multi-view input. So if you have multiple cameras, like 2 to 4 cameras, it can't directly leverage this information. That brings us to multi-view 3D point tracking. Because it has multiple views, it has a better coverage of the scene, which can then bring better precision, which is important for all applications. However, it's only been studied so far with optimization-based methods, which would require many cameras, for example, 27 cameras or 100 cameras in some setups. Or other methods that are optimization-based would rely on the monocular priors from monocular 3D point tracking and depth estimation. This is why we introduced the first feed-forward multi-view 3D point tracking method. We call it MVTracker, and it runs at 14.9 frames per second. It can work with as few as, for example, 2 to 4 cameras and already have benefit from the higher precision. and directly leverages and learns a prior on the multi-view input. The design we have also enables us to set the state of the art on the multi-view and monocular 3D benchmarks we have. At the core of our method is to take the different cameras and fuse the features from each cameras into this 3D point cloud. So we are working in this space. We'll lift the features in 3D to get this point cloud, and this is at the core of our method. This is a visualization of the features as using PCA to get colors. And on top of this feature point cloud, we'll learn a data-driven prior using a transformer. For this, we also contribute training as well as evaluation datasets for multi-view 3D point tracking. And our method, due to the design, which we'll discuss, is flexible to the number of cameras as well as how these cameras are arranged in space and what kind of depth is used. Compared to previous methods, which worked computed correlations in a triplanes, we work directly in this 3D space and instead compute the k-nearest neighbor correlations. So the problem we're working on looks like this. We're given RGB videos as input as well as the depth maps. And we also, for simplicity, assume we have a camera setup which is calibrated, so we know the poses and intrinsics. Then our method would run on top of this to get the output here on the right. So the depth maps can either be estimated or from a sensor. If we estimate it, we use Duster, VGGT, or other methods. In the output, we predict the trajectories of how each of the points of interest moved over time, as well as whether they were visible or not at a particular time step. Visibility means if the point perhaps was occluded in some or all of the views, so it was not visible at that particular time step. So let's look into details. We start as input with 3D query points, which define what points we want to track. We also take the videos, the RGBs, as well as the camera parameters, the intrinsics and the extrinsics. We'll run the RGBs through a convolutional neural network to get feature maps, which are discriminative enough for the task we are solving. And we either use off-the-shelf depth estimators, such as the VGGT or Duster, or if we have sensor, we can use sensor depth, for example, Kinect depth, to get the depth maps. We'll then combine these two by lifting them to 3D and associating each of the points from the depth maps with a feature map, feature vector, to get this point cloud on the right. So this point cloud is changing over time, and we have one for each time step. To do the tracking, we initialize the trajectories, the features, and the visibilities. And then the main part will happen in the transformer. So we're preparing now the inputs. First, we start with an initial trajectory prediction. In the beginning, it's just we repeat the initial location of the point, and then we'll refine it until we get the final trajectory. And to get the information necessary for tracking, we'll find the nearest neighbors around the current predictions of the point locations in 3D. So k nearest neighbors, where k is 16, and at different scales. And then we'll feed in these correlations with the current point feature and the neighbors, together with the current point predictions and visibilities into the transformer, which will update, give a residual update for the positions as well as the features. So the features can also change over time. For example, if the illumination changes, etc. And then we'll do this iteratively. We do this 4 times using the transformer to refine and update the trajectories and get the final output. What I showed you works on a window of 12 frames. To run the method on longer videos, we use sliding windows. where we initially run the method on the first 12 frames and then shift the window by 6 frames and then run it again with an overlap of 6 frames. And we do this also until we reach the end of the video. So for example, here it was 3 windows and the method runs at 14.9 windows per second. Compared to different sets of baselines, including optimization-based methods and 2D point trackers, as well as 3D point trackers, and a multi-view triplane baseline, which extended spatial tracker to multiple views. We perform best on the evaluation benchmarks. So this is the test set of Kubrick, and these are the unseen domains, DexYCB and Panoptic Studio. Higher means better. Average Jacquard is a metric combining whether the point was predicted accurately within a threshold of, for example, 5, 10 centimeters, 1, 2, 4, 8, 16 centimeters, for example, and also whether the point was visible or not. In terms of error, the median trajectory error, for example, on Kubrick is about 7 millimeters. On DexYCB, it's about 2 centimeters. If we use estimated depth, with Kinect depth, it's 8 millimeters. And on Panoptic Studio, it's about 3 centimeters. Panoptic is a larger scene. Due to the design of our method, where we fuse everything into this fused 3D feature point cloud, we are able to work with different number of views. So starting with 1 view and then increasing the views, we'll get better performance because we get a better coverage of the scene. So we start at about 64 points. With 4 views, we are at about 71 points in average Jacquard, and then it goes up to about 80 points with 8 views. Also, we can work with different camera configurations. So depending on how these cameras are arranged in 3D space, we can have, for example, these placements A, B, and C on Panoptic Studio and DexYCB. And no matter this configuration, we get stable results, which are also much better than the best compared baseline. Here are some visual results. On the top, we have the ground truth. And then next to it on the right, top right is MVTracker, our method. The red lines indicate error compared to the ground truth. And at the bottom, we have some of the strongest baselines. So spatial tracker version 1 is a 3D point tracker. And then the triplane baseline, which is a multi-view method. It's another sequence. So this is on DexYCB, on Dexter's manipulation dataset, where we are tracking points on the hands and on the objects. Our method can also work with different kinds of depths. So we have depth maps that are, for example, simulated, which we also use during training. We get these kind of results. So this is on Kubrick, on multi-view Kubrick. So it's very accurate also because the depth is so good. So it's much easier to do the tracking. Similarly, if we have a Kinect depth, we'll get average error of 8 millimeters. So this is, for example, a sequence of DexYCB, also a visualization of the feature point cloud, which we use to associate the points. However, if we don't have any high quality depth, we estimate it. For example, using Duster, we get these kind of depths as output, and this depth is of very jittery. This is still a very difficult problem for the reconstruction. And this degrades the tracking performance significantly. We are somewhat robust to the noise and jitteriness, but it would be much better if we can get a better depth. To show you how this can work with very high quality depth, here's an example of studio capture depth, which is a very high detailed and accurate depth. And there we can get results as these. And here's another sequence of also with studio capture depth. So to wrap this up, we introduced the first method that learns the data-driven prior for multi-view point tracking, and it's based on fusing the information from different cameras into a single 3D feature point cloud space. Because of this, it's robust to the number of cameras, the way the cameras are rigged, and also to the noise and source of the depth. We have significant gains on all the data sets compared to baselines. However, the method is currently very dependent on the depth estimator, and this field is still evolving. We hope to see improvements there and also work on it and maybe combine the two. We also didn't test on unbounded scenes, so most of the scenes and datasets we worked with here are bounded, and generally more data would be better. Currently we train on static data, so on Kubrick, more data would always be helpful for training. That's also, this is a very short introduction to multi-view point tracking and a presentation of our work. I'm happy to take any questions and discussions now.
Okay, thank you very much. Well, I have two questions already, quite practical. Like, do you know, maybe you didn't did it yourself, but do you know if there are more modern techniques than the charcoal board to do the post calibration?
To do post calibration with in general, or
yeah, in general,
or with point tracking. So there are 3D reconstruction methods like VGGT that can estimate the depths, or you can use right call map and the classical tools to estimate the poses of the cameras. Is that what you're referring to, or?
Yes.
So do you have just the images of some images without any calibration of the cameras, or do you also have calibration of?
Like, I was wondering, in the dataset you presented, do people use a special procedure to do the calibration, or do they use maybe, like you said, call map or charcoal board? Or?
So in the training dataset, it's the simulated depth, and so we have everything accurate.
Okay, yeah.
For the other two datasets, I don't know the details of how they estimated it, but they provided it in the dataset.
Okay.
I don't know what they used. Probably some classical techniques, yeah.
And so when you showed the benchmark is a simulated benchmark?
No, just one of them, just the Kubrick. XYCB,
okay.
So the...
Yes. So
yes,
how is the benchmark generated? Like, how do you get the annotations, proper annotation for the benchmarks?
So for this one, it's in Blender. Oops, sorry.
Yes.
And so there it's easy. So everything is just a simulation. And for the other ones, people annotated the objects. In this data set, we have annotations of 6 degrees of freedom poses of each object. So we also have poses of objects as well as annotations for the hands.
But so people annotate the 3D data or 2D data? They annotate 2D data?
I don't know the details.
Okay.
Probably a combination of both.
Yeah. And also, you said you use Duster to get a 3D point cloud from, like, does it work with very few cameras, like 3 or 4 cameras, Duster, to have a reconstruction, 3D reconstruction?
I think it depends a lot on the data. So on some data, it can work really well. For example, this data set struggles a bit more because I think the setup is a bit unusual with this black background and table.
Yeah.
So it depends a lot on the data. If it's more similar to the training distributions where Duster works better, then it can work very well with 2 to 4 cameras. But yeah, in our case, it didn't work very well.
Okay.
So we get this jittery output.
Thank you. And how long does it take to get a reconstruction with Duster?
It's under 1 FPS. It's not fast, maybe 0.1 FPS. So it's basically slow. If we use Duster, then we can't run in real time or near real time.
Okay, thank you very much.
Other methods, like newer methods like VGGT, are faster.
VGT?
Yeah, this can run at 2 or 3 FPS in our setup.
Okay. Thank you.
No worries.
Okay, yeah. So that's all I had as questions for me. Is there any other questions in the audience? Ivan?
Yes. So you've used Duster. I had a question. How does the quality and the FPS of the camera influence on the usage of Duster?
Duster works only with 512 maximum size generally, so it's been trained only onto like with a longer length of 512 pixels. So even if you have a high quality camera, it would get downsized and downsampled to 512. So you don't need to have a very high quality camera at this stage to use, for example, Duster and these methods, because they generally work with lower resolution images anyways.
And also, did you try
which could be improved
to compare master and Duster? And why didn't you use the master instead?
I think at this time, yeah, I think it was released. I think we could have also used it. Master is different mostly in that it also adds this matching head, so you could technically run, for example, master SFM or some SFM in the loop. But this could be very, very slow then to estimate on each sequence, because you need to run also like callmap or SFM methods to get. So we did compare other methods like VGGT, and I'm not sure if we in the supplementary in table 1 or 2, I think there's a comparison between different depth estimators. So Duster and VGGT and sensor depth.
Thank you very much. Any other questions?
Yeah, I have another question. So I wasn't here from the beginning of the presentation, but I understand that your project worked with fixed cameras, right? And you have the intrinsic and the extrinsic parameters of those. And my question is, about the fixed part. Let's imagine you have the coordinates, all of the data during time of the camera, and the camera, for instance, revolves around the subject or anything else. Would it still work, or like how far are you to make this adjustment?
You could run the method directly in this setup, yeah. We didn't focus on it specifically. We mostly focused on like 4-view evaluation and with static cameras. But the method directly can work with this as well, with that setup. So you could run it directly on that configuration.
Okay, thank you.
No worries.
Okay, if there are no further questions, thank you very much again, Frano. It was very interesting. And if you happen to be in Paris, don't hesitate to give us a visit.
Thank you. Yeah, sure. Makes sense. Thanks a lot for inviting me. It was a pleasure to give talk.
Great. Thank you.
Nice.
Goodbye.
Bye-bye. Thanks.
Thank you.